remember this F has got compact support. That means it vanishes identically outside some big ball centered at the origin. So we can write an intersect BR0 here, where BR0 contains the support of F, a set of points where F is not 0, closure of a set of points where F is not 0. So just pick any big R, doesn't matter. Just pick an R large enough so that that's true. And then let's rearrange this a little bit. Notice this is the same as eta x lambda of m minus nj intersect, if I put a bracket there, and remember eta takes the ball of radius r to the ball of radius lambda r. So this is the same as applying eta x lambda outside the bracket to that set, right? Because eta x lambda translates x to the origin, so it takes that ball centered at x to a ball centered at 0, and it multiplies by lambda to the minus 1. So it takes the ball b lambda r to the ball br. So you get back to this. So it's the same as that. Times hn. That. And now we've got to remember the definition of Hausdorff measure. I'm not sure I mentioned this before. But if you look at the definition of Hausdorff measure in Euclidean space, you'll see that it scales appropriately. That is, if you take the, first of all, it's invariant under translation. So the Hausdorff measure of the translated thing is the same as the Hausdorff measure of the original thing. And it scales appropriately. And when you scale, that means you get a factor lambda to the minus n times the unscaled stuff. Because we're talking about n-dimensional Hausdorff measure. So this is equal to sup mod f times lambda to the minus n times the Hausdorff measure of the unscaled thing. That's m minus nj intersect b lambda r x. So that's an important point. It's one of the basic properties of Hausdorff measure in Euclidean space is that it's got this scale property. That it scale. If you scale the set by a factor of lambda, then it scales the measure by a factor lambda to the n. Or in this case, we're scaling by a factor lambda to the minus 1, so it scales the measure by lambda to the minus n. Now stare at that for a minute. You remember this is covered by one of our basic theorems, the upper density theorem. The upper density theorem says that this tends to 0 for hn almost every x in nj. But that contains mj. So certainly for hn almost every x in mj, this tends to 0. This is by the upper density theorem. So that's nice. That's a nice application of the upper density theorem. So that means this indeed does tend to 0. Okay. That tends to 0. And similarly, almost identical argument says this bit also tends to 0. So similarly, this guy tends to 0. For hn almost every x. Hn almost every x in M this time, which of course again contains mj. So in particular for hn almost every x in mj, that tends to 0. So both of these terms tend to, so this tends to 0, this tends to 0. And this guy, well, that's easy. The nj is a classical C1 manifold. So this guy just tends to the classical integral of f over the classical tangent space of nj. So let's do that. So, yeah, let's write it here. Integral e to x lambda nj f thn tends to the integral over the classical tangent space x at nj f thn for every x in nj, which again contains mj. So that term tends to the integral over the classical tangent space. So let's put all these things together. So this tends to integral over tx nj f thn. So that's it. This guy tends to eta x lambda m f dhn tends to the integral over the classical tangent space of n f dhn for hn almost every x in mj. So that's that. By the way, so that's the end of the proof. So, by the way, notice there's some subtlety here. This is not a misprint. TXM, not TXMJ. TXM exists for almost every x in MJ, and it's equal to TXMJ. Okay, so that's important. That's a very important lemma. But now certainly the most important result here is that you can give yet another characterization of countable rectifiability, namely, here. So same hypotheses. Let's just call this. We'll keep you. So we're assuming this always from now on. Locally finite and Hn measurable. So assume star. Then M is countably n rectifiable if and only if Txm exists Hn almost everywhere. Almost every x in M. That's the equivalence. Very nice characterization of rectifiable set. And we'll see in a little while this lemma together with that, together with the thing we just proved, will enable us to do various things like take directional derivatives and take gradients and use the area and co-area formula. Various other analytic tools will be available on rectifiable sets now rather than just on smooth manifolds. So let's give the proof. Well, let's do it's two things to prove. So this one we've already proved. This direction is the lemma. That's that lemma. In fact, this lemma gives a bit more information. It even tells you this additional information about the approximate tangent space. So let's give the other direction. Now, this is interesting. Most of the things we've done to date have been sort of not particularly deep. They've been more or less just following definitions rather carefully and seeing what we can deduce from them. This is one of the first times we've come up against something where it's not at all obvious how to proceed. I mean, think about this. We've got to prove that if the approximate tangent space exists almost everywhere, then M is countably n rectifiable, meaning that that you can write it like this. It doesn't seem at all clear how you would even start the proof of that, right? So you should be aware this is a slightly different level of difficulty than we've been encountering most of the time up to this point. So we have to work out how to proceed. Well, obviously then we have to look pretty carefully at the definition of approximate tangent space. So let's do that. Well, here's the definition of approximate tangent space. And it seems pretty clear. Let's use our standard notation here. This is Txn. It's pretty clear that we can get lots of information by just taking special choices of f. After all, this holds for every f, which is C infinity with compact support. So it seems pretty boneheaded and straightforward that we should try some special choices of f and see what information we can glean from that. This is a basic idea from PDE and analysis generally. If you study, for example, quasi-linear elliptic PDE, there's something called choosing the right test function there. It's sort of an art form that you can use to get lots of results just by choosing a particular function. And this is analogous to that. We want to make some special choices of functions. Well, I claim that if we make the right choices of these functions, then we can immediately deduce a couple of things initially. So I claim two things, actually. First thing is that Hn of m intersect b rho x over omega n rho to the n, I claim that that tends to 1 for Hn almost every x in m. Notice that's in our previous notation when we were talking about densities in measure theory. Notice that's the same as saying that the density, the n-dimensional density of the Hausdorff measure was restricted to m at a point x is equal to 1 for Hn almost every x in m. So that's the first claim, that you can say that. The second claim is that you can also say a similar density fact, but instead of using just a ball here, I'm going to intersect with a slightly more exotic set. Let me introduce the notation for that. So notation. Suppose that alpha's between 0 and 1, and pi is any k-dimensional subspace of Rn plus k. So that means the orthogonal complement then is an n-dimensional subspace of Rn plus k, right? And I'm going to let x alpha of pi x be the double cone that you get by taking points at distance less than alpha times their distance to pi being less than alpha times their distance from x. So in other words, this is the set of y in Rn plus k such that the distance of y minus x to pi is less than or equal to alpha times the distance to the origin, or distance from y to x. And that looks like this. So this is pi, and then pi perp is here. Pi perp is n-dimensional, pi is k-dimensional. And let's see, let me do a sort of a three-dimensional picture at least. So this would be a circular cone. circular cone with axis equal to this k-dimensional subspace. And this angle here, if we call that angle theta in that right triangle there that you get by taking, it's a right angle there. That angle theta is distance over that. This is the distance of the point. If this is y, then this is the distance of y to the perp, and this is the distance y to the origin. So it's arc sine, isn't it? This angle here, theta, this angle is theta equals arc sine of alpha. But remember, we're talking about all of the points inside, not just the points on the boundary. This is less than or equal to, it's all of these points inside. All of these points inside this cone and in the lower half too. It's a double circular cone. So that's the notation we're going to use. And the claim is, the second claim here, is that if you've got, if TXM exists, so I should have said, the claim is that if TXM exists, and the first thing is this, that's the first claim. And the second claim relates to these cones. The second claim is that HN, M intersect the cone, which is, let's agree that we let pi x be the orthogonal complement. So let pi x be the orthogonal complement of the tangent space. Notice that's k-dimensional, because the approximate tangent space is n-dimensional, and we're in Rn plus k. So that's a k-dimensional subspace. So let's agree to call pi x that Tx m perp. And at x, always take vertex at x, then the claim is that that intersect b rho x over rho to the n tends to 0 for Hn almost every x in M. And I think you can sort of get, I mean, if you just think intuitively, I think you can see that both of these should be true, actually, without doing too much work, because M is here, could be a nasty-looking thing. It's only got an approximate tangent space after all, so it could be terrible-looking thing, but at least it's got this approximate tangent space. So the picture would be that. And if you're in a sufficiently small radius, the definition sort of suggests that up to a set of small measure, this is almost equal to a disk of the that you get by taking the n-dimensional ball intersected with the n-dimensional subspace. You get an n-dimensional disk. So it looks like this ought to be true. And it also looks like this ought to be true, because there shouldn't be much measure that can intersect up into this conical region, because most of the measure's down here close to the plane, you see? Close to that. On the other hand, we do have to prove it. We can't just draw a picture and claim it's true. But it's actually rather easy to prove number one. Let's check that. So let's check one. As I said, the trick is to take special choices of f. Well, clearly we want to take f that's almost equal to an indicator function for the ball, because we're interested in m intersect b rho. And you get m intersect b rho if you took f exactly equal to the indicator function of the unit ball there, because this is just a rescaling. So take f. You would like to take f to be the indicator function of the unit ball, but the indicator function of the unit ball has got a discontinuity on the boundary of the ball, so you can't do that. So you've got to use an approximation to the indicator function of the ball, right? So take f as follows. You take f to be a function from Rn plus k into the unit, into the interval, in the closed interval 0, 1, and you require that f is identically equal to 1 on the unit ball centered at the origin, and you take f to be identically 0 outside the ball of radius 1 plus epsilon centered at the origin. Now that you can do. You can certainly cook up a continuous function which is identically 0 on the unit ball and which is identically 0 outside the ball of radius 1 plus epsilon and is identically 1 in the ball of radius 1, and which goes down sort of linearly to 0 in between. So you can certainly do that. And then you see what this gives you. Well, we know that we're given this tends to that, so integral e to x lambda m f tends to integral e to x lambda tends to the, by definition of tangent space, this. And now let's think about this. What can we say about this? Well, this number is a number for each given f. That number is between, it's certainly bigger than, let's take, I want to divide by omega n here, each side. And then let's look at that ratio, that number. Well, that number certainly bigger than or equal to 1, because because f is, see, this is bigger than or equal to the integral txm intersect b1, because f is bigger than or equal to the indicator function of the unit ball, right? So it's certainly bigger than that over omega n. But then that's of 1, right? Number 1, thn. But that's bigger than or equal to, this is just the volume of the unit ball in Rn, right? It's an n-dimensional subspace intersected with the ball, radius 1, so that's omega n again. So this is equal to 1. It's equal to 1. So it's certainly bigger than or equal to 1, and similarly it's less than or equal to 1 plus epsilon to the nth power, because it's less than the integral of 1 over the ball of radius 1 plus epsilon, because f is less than or equal to 1 everywhere on the ball of radius 1 plus epsilon, and is identically 0 outside the ball of radius 1 plus epsilon. So this is less than 1 plus epsilon to the n and bigger than or equal to 1. So we're making some progress. And now, on the other hand, what about this guy? We do a similar estimate for the right side here. So let's do that. Oh, I don't think I want to do that. So, yeah, so let's get this back. So let's see. Yeah, so this side's between these two numbers. Now this side similarly. Let's check that. So integral e to x lambda mf dhn is bigger than or equal to bigger than or equal, let's see, f is bigger than or equal to 1 on the unit ball. So this is bigger than or equal to hn e to x lambda m intersect b1, 0 over omega n, this over omega n. And it's less than or equal to 1 plus epsilon to the n times 1. Again, f is less than or equal to 1 on the ball of radius 1 plus epsilon. Less than or equal to, f is less than or equal to 1. So it's just a factor of 1 times the hn e to x lambda m intersect b rho, b1 plus epsilon, 0 over omega n. And now we just do we just use the scaling properties again of Hausdorff measure, as I mentioned before. So this, remember, scales like lambda to the minus n. So this is implies that lambda to the minus n. So you get a factor lambda to the minus n, and you translate x to the origin, and the unit ball becomes the ball of radius lambda. So you get hn m intersect b lambda, centered at x now, over lambda to the omega n lambda to the n is less than or equal to this, is less than or equal to, and again, similar argument here, except that this time we're talking about ball of radius 1 plus epsilon, so we'll get a factor 1 plus epsilon to the n. Otherwise the same, so we get hn m intersect, now it's lambda times 1 plus epsilon now, centered at x, over omega n lambda to the n. So that's what we get. Well, now you just put these things together. You see that this clearly says that the difference between the number 1 and this integral is less than a constant just depending on epsilon, which tends to 1. So, in fact, if you work it out, you'll find the difference, eta hn m intersect b lambda x over omega n lambda to the n is, well, it's bigger than or equal to 1 minus, it's bigger than or equal to 1 over 1 plus epsilon to the n times 1, and it's less than or equal to, the other inequalities involve the ball of radius 1 plus epsilon. So that's good for that one. And then the other inequalities involve the ball of radius 1 plus epsilon. So they're less than or equal to, I guess I got this wrong. This is, let's see, let's try again. Okay, so this, what's this? This is less than or equal to that, which is less than or equal to, which is less than or equal to that. This tends to, so it's less than that plus epsilon for small enough lambda. So that's, sorry, let's try again here. So using that inequality, that's less than, this guy is less than or equal to 1 plus epsilon for lambda small enough because of this fact. And using the other inequality, this one, it's hn m intersect, this is b lambda x, sorry. Hn m intersect b lambda times 1 plus epsilon x over omega n 1 plus epsilon to the n lambda to the n is bigger than or equal to 1 minus epsilon over 1 plus epsilon to the n for small enough lambda, for lambda less than some lambda 0. So you just put the things together and you get those inequalities. Now notice here, this is the same as lambda. We've got a lambda in each place. I've just put the factor 1 plus epsilon to the n in. So this is the same. Actually, we've bounded this quantity both above and below, right, as lambda is small enough. So what we've actually proved there, you can check this for yourself, that is, we proved that we proved 1, in fact. This tends to 1. Okay, so that's not too complicated. You just have to pick the right function f in this way. Now this one's a little bit harder, but the same basic idea. And that's one of this week's problems, actually. So I'll leave the slightly harder bit to you, but it's basically the same sort of idea. So let's take this as a given then. So we've got both 1 and 2 to work with now.
So are these equal to the existence of approximating the space? These two conditions?
No, they're not. No, they're implied by, but they do not imply. Yeah, of course. They don't imply because you might have some squelched up thing that just happens to have density 1 at the point. You see, even though it's not getting close to a you can, well, I assume you can cook up examples like that. I didn't actually do it, but I'm pretty sure you can cook up examples like that where you've got both of these properties. Well, actually, 1 certainly is, yeah, well, actually, no, I'm not sure, actually. Maybe it's not so clear. This may imply, if you know this for every alpha positive, certainly almost everywhere, it would imply the thing, but I'm a bit worried about exceptional sets. I don't know the answer to your question. Yeah. Okay, so okay, so we do have these two things to work with, and that's good. So at least we have something to work with now. But it's still far from clear how the approximate tangent space existing, even after we've proved these two things, which is sort of encouraging, it's still not at all clear how we're going to cook up these Lipschitz mappings, or alternatively these C1 submanifolds that appear in the definition of rectifiable set. So we still have a certain amount of work to do. So let's take a break, and I'll show you how to do this after. Yeah, I'm not really sure about that. That may actually be right. Well, it may be right if you assume that for every alpha. Otherwise, it would be in almost every result, I think. In fact, yeah, it's certainly in almost every result, because we're only going to use these two facts from now on in the proof. Yeah. So it's certainly in almost every fact, but I'm a bit dubious about whether it's everywhere. You were back. I've been on a couple of hard walks. They've almost crippled me. So. We went to Taroko Gorge and did the hard walk there. That was fantastic. Yeah, fantastic walk. Yeah, parallel to the river, but vertically down. Mao-Pei.
Yeah, it was very nice. Yeah, we applied the permits earlier. Mm-hmm. Yep. So you also walked a lot yesterday.
That's right.
I saw a picture. Right?
That's right, I did.
But the yesterday was pretty nice.
Yeah. Yeah. Hmm. Yeah. Where were you? You were traveling? Uh-huh. 10 days, nice. Right. Do you do something like that each year, or? Okay. No, I don't know that I have actually. See, the last time I was in Taiwan was 25 or 30 years ago. I don't really remember where I went. A bit too good, I think.
No, I'm not.
Taiwan we call 100
No. I'm very wary. Both of you guys, I'm extremely wary.
Because something
Oh, right. Right. I would like to do some more, but I'm a bit worried about you. You're a tough guy. We definitely should do another walk, though.
Oh, since you come to Asia and come to Taiwan, maybe next time just join in Taiwan.
Yes.
But let me know.
Yeah, okay. Okay. You could arrange a particularly hard walk.
So for some 3 days or 4, that kind of thing.
Right,
So you
okay.
have to sleep on the mountain,
All right.
sleep in the mountain
Okay.
and so on.
I could probably take it. Maybe.
Oh, but by the way, he's also good.
I know. He was also looking a little bit threatening. Right.
So you drop there. Oh. Lots of exercise over the break.
Right. I at least compensated for all that exercise slightly by drinking beer. Yeah. I don't think so. I think we'll leave everything there, actually. Things are pretty grim now. We're leaving everything.
Everything.
May I ask a simple question? Except HN almost every field are kind of different. How different is the lift function from C1?
Well, I think that's the Rademacher theorem that says that the Rademacher theorem and the C1 approximation theorem. Rademacher says that it's classically differentiable almost everywhere. So means it's got a classical, the graph has got a classical tangent plane almost everywhere. That's one point. And the second point, of course, the trouble is that doesn't mean it's continuous, that tangent plane. It's discontinuous at various points and could be discontinuous on a set of positive measure as well. But on the other hand, you can take a C1 function which sticks to the Lipschitz graph, rather a C1 function whose graph sticks to the Lipschitz graph except for a set of small measure. So that's about the best you can say. And you can make the set of small measure as small as you please. But every time you reduce the epsilon in that small measure, the C1 function gets slightly worse behaved, right? So you can't sort of pass to the limit and get a set of measure 0.
So in some sense, this problem is some question is some kind of major theoretical.
Yeah, I'm
Maybe
afraid.
some kind of course, I'm
Yeah,
special, but
yeah.
some kind of non-concept.
Yeah, no, that's right. I think the way to think of it is that you've got a C1 function except for a set of small measures. Yeah, yeah.
He said that is not true.
What?
He said that is not included.
Oh, okay. Oh, you've got a counterexample.
Yes.
Yeah, 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 yeah,
The
yeah.
parabola.
Yes,
Yes. So
yes,
you do like this.
yes,
You have density equal to 1 and 0.
yes,
And if you fold it here,
yes.
you get a set result.
Oh, okay, good. Thank you. Very good. Oh, very cool. Yes. Extremely cool. I like that. I was thinking of some pathology.
Something more complicated.
Right. That's great. Yeah, I think we can get rid of this now. Okay. So let's continue. So we have these two properties. Now the rest of the proof will just use these two properties. By the way, Joe just gave a nice counterexample to show that these two properties are not enough at every point to prove there's an approximate tangent space. Joe's example is that you just take a one-dimensional example of a curve, parabolic curve, say, together with another curve. Notice that's at that point, that's got density 1, satisfies this, and it's also got this property. So that counterexample doesn't have to be pathological. It's just a nice example. I probably should add that one to the text. Okay, so the rest of the proof will just use these two, and we want to prove we want to show that the definition of countably n-rectifiable is satisfied using these two things. So, how do we do that? Well, the first thing that we do is to notice these are two limits, and Egorow's theorem has something to say about that. If this is true almost everywhere, then Egorow's theorem says that these limits are uniform except for a set of small measure. So let's use that first. So I've got to make sure everything's finite, so we'd better just take any r bigger than 0 large enough to ensure that H and M intersect B rho 0 is positive. Just for technical reasons, just to be the open ball. So for technical reasons, by the way, if H and M is 0, there's nothing to prove, right? That means trivially by definition. So assume that H and M is positive, maybe infinite, but assume it's at least positive. Otherwise, nothing to prove. And take an R large enough so that that's true. And then take the Borel regular measure that you get by restricting Hn to this set. So let mu be the Borel regular measure that you get by restricting Hn to this set. Now, so that's a finite measure now. Notice that that's finite because we're intersecting with M. And remember, we are assuming that M has got locally finite measure on every finite measure on every compact set. So this is finite. So then mu Rn plus K finite and positive. So that's just technical step to set things up. And now I'm going to use Egarov's theorem to make these into uniform limits. So by Egarov, the limits there exist. So let epsilon be positive. No need to do that. By Egarov, there exists a set E, a Borel set, E contained in Rn plus K, which chews up some fixed proportion of the total measure, let's say Rn plus K minus E less than a half of the total measure. We don't have to be too precise because I'm going to set up an iterative process later so that a factor of a half is good enough to ultimately prove measure 0. We'll show that we can, as long as we chew up at least half the total measure. So we do that first, such that Egarov guarantees that you can pick such a set such that the convergence here is uniform. 1 and 2 are uniform. For x in Rn plus K minus E. So you get uniform limits there. And right. So you get uniform limits, and in particular, I'm going to throw away some information now. So what does uniform convergence mean? It means that for every epsilon bigger than 0, there exists a delta bigger than 0, which doesn't depend on the point x, such that you're within epsilon of the limits, right? So let epsilon be bigger than 0, then there exists a delta bigger than 0, such that, now I'm going to throw away some information. I could actually say that the difference of this absolutely is less than epsilon, but I just want the lower bound on this. So such that Hn m intersect, this is our new measure mu, so I don't have to keep writing all this stuff, just mu. Mu b rho, I can write it as mu m intersect b rho, that's probably a nicer way to write it. B rho x over omega n rho to the n is bigger than or equal to 1 minus epsilon for every rho less than delta, and for every x in Rn plus K minus, for every x in E. Oh, sorry, wrong way around. E is the set where the uniform convergence is occurring. So the complement is less than a half, chews up at least half, and then the uniform convergence is on the set E. So this is for every x in E. So we have that. And I'm also going to, I could also say that this one is less than epsilon, but I just want the inequality going that way. So, well, that's actually the same in this case. So Hn mu m intersect x alpha. And I'm going to use this one. I'm again going to throw away a bit of information. We knew this one for each alpha, but let's just take alpha equals a half as a convenient. So take alpha equals a half. And so we're applying Egarov to the case when alpha equals a half here, right? So m x pi x x intersect p rho x over rho to the n less than epsilon. So we have those two things. And now, now comes the clever idea that it's a bit hard to motivate until you've actually seen the rest of the proof. So I'm just going to tell you what the trick is here. You first of all, you cook up, well, actually the next step is not a problem. I'm going to take, notice this is a compact, yeah. What is that noise? Oh, I see. Right. Uh-huh. Right. So I'm going to take. There's a problem in actually making use of this inequality here because this is jumping around. You see, it may be wildly jumping around as x varies. So I'm going to try to divide the space up into points where this is near to some particular k-dimensional subspace. So let pi 1 up to pi n be k-dimensional subspaces such that so take epsilon positive given, well, we've already done that, we've got an epsilon here. Let those be k-dimensional subspaces such that for every k-dimensional subspace pi contained in Rn plus k, there exists J with the distance from pi j to pi less than epsilon. So you can do that because the Grassmannian of k-dimensional subspaces is a compact manifold, right? So it's compact, so you can certainly do that. Just find finitely many k-dimensional subspaces which get close to every other k-dimensional subspace within epsilon. So do that first. And this distance here means sup mod x equals 1 of the you take the orthogonal projection onto, this is the distance between subspaces. You take the orthogonal projection onto the subspace pi j, subtract off the orthogonal projection onto pi j, and that's less than epsilon. So here p pi equals orthogonal projection of Rn plus k onto pi. So this is sup of that. Notice that's just the norm. It's just the norm of the linear map. Just the norm of the linear map. So that's our measure of distance between these subspaces. So pick k-dimensional subspaces which get close to any one of these things. Of course, the catch is which j works depends on which x you're talking about. So you've sort of reduced things down to a finite collection. And now here comes the trick. The claim is, this is a big claim because it's not very well motivated at this point, but you'll see when you see the proof, you'll see the idea. The claim is that with epsilon equals a suitable number depending on n, in fact 1/16 to the n plus 1. Wow. With epsilon equals 1/16 to the n plus 1, I claim that x1/4, now remember that's the cone with alpha equals 1/4. x1/4 of pi j x intersect ej. Oh, I didn't say what ej was. So I'm going to let ej be the set of x in E such that the distance of pi j to pi x is less than 1/16. So we've broken, notice then E is the, if we take this with 1/16, then you see E is then the union. It's not a disjoint union, but it's a union nevertheless. J equals 1 up to n of EJ. So the union of the EJs does give you all of E. So we've broken E up into the points where pi x is suitably close to the jth pi, right? Got some good sound effects today. Right. Okay, so the claim is that if we do that, then the claim is that this intersect d delta over 2 of x. The claim is that this set, in other words, I'm looking at the intersection of EJ, that's this set here, with the small ball of radius delta over 2, where delta is this number. The claim is that that set does not intersect this cone at all except at the vertex x. Now that's far from obvious, but that's the claim. That's the main step of the proof. You claim that because of these uniform properties here, the claim is that if you take epsilon equals small enough number, and this would be a good number, 1/16 to the n plus 1. Ah, that's better. Right. Yeah. Yeah. I somehow I can't handle white. I can't handle white noise. It's, so the claim is that this is true. So in other words, this is the claim that if you take this is pi j, and here's x. The claim is that if you work inside a suitably small ball of radius delta over 2, then there's none of EJ. EJ is some set here. EJ can't do this. That's not allowed because you've got points inside the cone there, you see. So the claim is that doesn't happen. The claim is that this is the picture. Where's that colored chalk? Yep. Claim is that EJ does this. May look pretty bad, but it doesn't get up inside the cone. That's the claim. Now let's check that. I tried to think of a way of motivating this, but it's better just to state it and then check the proof, and then you see why it's true. So check. So let's check that. Okay. Otherwise, there would be a point y not equal to x, which does get up into this cone. So otherwise, there exists a y which is in this set, y not equal to x, in this set, x 1/4 pi j x intersect EJ intersect b delta over 2 x. And let's let rho equals the distance. Notice that is a positive number because y is not equal to x. And it's a number that's less than delta over 2, furthermore. Okay, and then you sort of draw a picture to motivate the next bit of the argument. So then we would have this sort of picture if it's really false. Have a point y here. So y would be there. And we're taking rho to be this radius. So I should draw an enlargement of this. So this is central axis is pi j. EJ is coming here, and we're assuming that it fails this test. It comes up into here. And this is radius rho. Radius rho. And delta is out here somewhere, at least twice the radius. Then the claim is that then if that happens, then I'm claiming that B rho over 8 centered at that point y is contained in the cone with angle 1/2, with alpha equals 1/2, pi x, x, notice not pi j, pi x, intersect b rho x, b2 rho x. So I claim that, so the claim is that the ball of radius rho over 8, that's this ball, rho over 8, centered at y, would be contained in, so then pi x, remember pi x is within, is close to, it's within 1/16 to the n of pi x, within 1/16 of pi j. So this would be pi x. This is, of course, this point here is x. That doesn't change in this part of the argument. This point here is y. So I hope that's clear. That's, the claim is that that's contained in, so I haven't finished drawing the cone, pi x. So pi x, maybe I should use a different color. Right. Does green show up? Does anyone know? If I do it in green, is that a bad idea or a good idea? It's a while since I used colors. So the claim is that if we use this as our central axis, that's pi x, then the cone of radius 1/2 contains this. Whoops, didn't do that too well. Yeah, 1/2 wide, I think. So this is x 1/2 pi x x. It looks sort of convincing on the picture, right? But we've got to check that using some inequalities now, right? So that looks convincing, but that's true. So let's check the inequalities to make sure. So, right, so we want, we've got to take a point z in here and check that it's also in here, right? So take, so z minus y less than or equal to rho over 8. That means we're looking at a point z in this ball. That implies that now we can look at the distance from z minus x to pi x, because we're trying to prove, see, it's here. We're trying to prove it's in this set. So we should look at this distance. Okay, well, that's equal to d y minus z minus y, yeah, z minus y plus y minus x to pi x, and that's less than or equal to the distance of z to y, which is less than rho over 8, plus the distance from y minus x to pi x. And that's now, yeah, so that's rho over 8 plus, now this distance is exactly, by definition, y minus x minus the orthogonal projection onto pi x of y minus x. That's what the distance to a subspace is, right? It's exactly the distance to the subspace. And this is less than or equal to, well, we still got this rho over 8. And y minus x is less than y minus x. What do we know about that? That's less than, y minus x is rho. So this is rho. That didn't seem to work out too well. Oh, yeah, that's not right. Okay. Yes. Okay. Yes, I'm sorry, I forgot. We're not using our information. Y is in here. So I want to say this is less than or equal to rho over 8 plus y minus x. And now I'm going to put a p, I'm going to replace this by p pi j, because I want to use this fact that y is in here. So I want to do a plus y minus x minus p pi j y minus x. But then I've got to add that, that's an error. I've got to correct that. So I put in p pi j minus p pi x y minus x. Like that. And now use the triangle inequality. This bit is less than or equal to rho over 4. Rho over 4. So this is less than or equal to rho over 8 plus rho over 4. Yeah, because, right, p pi y minus x. Quarter, right. Yeah, the distance is less than a quarter, that's right. That distance there is less than a quarter times the distance to the origin. And the distance to the origin is rho, so that's rho over 4. So this bit is less than rho over 4. And what about this bit? Well, this bit is less than 1/16 times rho, so rho over 16. And I hope I did the arithmetic right here. So what's that? 4/16 plus 2/16 plus 1/16 is 7/16, right? Which is less than rho over 2. There we are. So less than, you're right. So that's exactly says that this this is in the cone of less than 7/16 times rho. I still don't think I did that right. 7/16 times y minus x, right? That's what we've proved. And that's less than, z minus y. Right, z is in the ball of radius rho over 8. So this is less than, rho over 8. Less than 8 times. Oh, I don't think I did do that right.
Right. It's on x1/2.
Yeah.
And then.
Yeah. So this is right, but we're talking about this point, right? C minus x. So I think I've got the constants messed up here. See, I'm supposed to get less than or equal, I want to get less than or equal to half z minus x, right? And what's z minus x? Z minus x is bigger than or equal to 7/8. Oh yeah, I did get it right. Z minus x is bigger than or equal to 7/8 of y minus x, because y minus x is equal to rho. See? By the triangle inequality, this implies that, right? 7/8. So I get 7 7/16. One should never have to do this. It's too embarrassing. Times 7/8 times 8/7. 8/7. Look at that. That's 1/2. Wow. Okay, so that proves this. So the picture is correct. Now, that can't happen because then the n-dimensional Hausdorff measure of x 1/2 pi xx intersect b rho, I think I want to take. Yes. No, I want to take b delta over 2, I think. Yeah, I do. B delta over 2. Oh, no. Yeah. Hn x 1/2 pi x intersect b 2 rho. I guess I want to take the ball of radius 2 rho. So I take the cone, intersect the ball of radius 2 rho, x. So notice the ball of radius 2 rho is out here somewhere. It certainly includes this now. So here's the ball of radius 2 rho. That's right. That pi x intersect b2 rho intersect m. That would then be bigger than or equal to Hn m intersect this ball of radius rho over 8 centered at y. By that inclusion that we just proved, this one. Yeah, there it is, 2 rho. So it would be bigger than or equal to that. But then we can use this inequality, rather this one. Where is it? This is certainly bigger than, epsilon is 1/16 to the n plus 1 or something. So this is certainly bigger than or equal to 1/2 anyway, with our choice of epsilon. So this, we can use this one now, except that we're using b2 rho instead of rho. So we get, this is bigger than or equal to 1/2 times omega n times 2 rho times, rho over 8, rho over 8. What? Yeah, that's right. We're using this with rho over 8 and with y there. So rho over 8 to the n, right, bigger than or equal to that. I think that's correct, yeah, that's right. 1/2 rho over 8 to the n. But on the other hand, this is less than or equal to, by this second inequality here, this is, we're using epsilon equals 1/16 to the n plus 1. So this is less than or equal to 1/16 to the n plus 1. It's got a 2 rho though, we've got to watch that. So 1/16 to the n plus 1 times 2 rho to the n times the, no, that's all. That's what the second in. I think I left off a omega n here actually. I should have put an omega n here, otherwise the inequality doesn't quite work out. So that's a typo, there should be an omega n there. So then that's less than 2 omega n. But notice this constant here is, let's see, 2 to the n, that's 8 to the n, 1/8 to the n times rho to the n times omega n. And you see that's ridiculous. This number here, oh, not so ridiculous. Yeah, no, it is ridiculous because there's an extra 16th here. Yep. So that's ridiculous. So that's a contradiction. So that's pretty tricky. I didn't think of it, but I think it goes back to maybe Federer, I'm not sure, who constructed this algorithm, very clever. But if you follow the pictures, it's sort of much easier to follow the rest, but the formalities do work out. And indeed, we have proved that this. Now, notice we haven't finished the proof yet. We've just proved this claim that this is just equal to x. No other. Here it is. So we've proved this. So this picture is wrong. It's actually the worst that can happen is that the set comes up. Maybe it touches. Well, in fact, it can't even touch because this is the closed cone. So this apparently must be the picture. Now, the rest of the proof is relatively simple. So let's talk about that. So okay, maybe I'll just manage to finish this. So now this is what we proved so far. Okay. Now, take any x0 and be, say, delta over 4. Remember, we've got this number delta from the Egorov theorem. We've got that fixed number delta centered at 0. See, hold on. Yeah. Take any x0 in EJ. So we've got this picture at the moment. Here's EJ, and EJ's got this property that all of these cones with axis parallel to pi j and vertex at a point x in EJ don't intersect EJ except at the point. So you see the picture? These are all parallel. These are all in the direction pi j. Because remember, EJ was defined in terms of the single k-dimensional subspace, pi j. It's the part of E that process works with. So you have that picture that so it's got this cone property that well, as long as you intersect with the ball of radius delta over 2, it's got that property. But see, there's a little catch here. If this is the point x we're talking about, then we've just said that this cone doesn't intersect the yellow stuff except at that point. But that's not quite true. That's only true in the ball of radius delta over 2. Centered at that. See, the problem is this could come around and do that. So we've got to take account of that. So we're going to take account of that possibility. Namely, take any x in EJ, and then any x in B delta over 4 x0 implies that sorry. This is just a bit too much for me, I think. It's just too complicated. Yeah, that implies that B delta over 4 x0 is contained in B delta over 2 x, just by the triangle inequality, right? Contained in B delta over 2x. So that means that, okay, we can get around this difficulty that I just mentioned just by taking the piece centered at some point x0. So we take a fixed x0 and work inside the ball of radius delta over 4 there. Then that is contained in B delta over 2, so then X in B delta over 4 X0 intersect EJ then implies that this holds with B delta over 4 X0 there, and it gets around the difficulty that I just described, because then we've got a fixed ball, fixed set. Implies that X, let's transcribe this, X 1/4 pi jx intersect EJ intersect B delta over 4 X0 is equal to X. Now that's much better. You no longer have this difficulty that I was referring to. Now the picture is that we've got our set here, and we take an X0 here and take the point of take the ball of radius delta over 4 around that. Then any point in there, any point X in there does have the property that the cone inside this this part of the set may intersect, but not this part of the set. So it does have a cone property. Has this cone property. Now stare at that cone property. Remember, we're forgetting about the rest of the set now. We're only looking at the part of the set in the ball of radius delta over 4. That's now got a uniform cone property. This is the cone X 1/4. This cone, X 1/4, in the direction of pi j with vertex at X. Every point X in the set has this cone property that the yellow stuff does not go inside the cone. Now think about that. Doesn't that say exactly that it's the graph of a Lipschitz function? It's contained in the graph of a Lipschitz function. With Lipschitz, what are the slope of these guys, by the way? Remember, these cones look like this. Pi j. This one is 1/4, so alpha is 1/4. So that distance is 1/4 that distance. What's the slope? Pythagoras' theorem, right? This is square root of 15 over 4. So the slope is less than or equal to the square root of 15, which is less than 4. So the slope of those cones are less than 4, and this part of the set has got a uniform cone property relative to that. That says that it's a Lipschitz, contained in the graph of a Lipschitz function with slope less than 4. B delta over 4 X0 intersect EJ is contained in the graph of a Lipschitz function with slope less than 4. And on the other hand, you can cover the whole set by finitely many of these balls. Remember, we're only talking about the part of the set inside the ball of radius R0. So that means that the conclusion is that is all of M intersect B, so mu of M intersect B hat 0 minus the a union, finite union of Lipschitz graphs. So we subtract off a finite union of Lipschitz graphs. Well, that takes away all of the set EJ. That takes care of all of the set EJ, and we can do this for each J, so that takes care of all of the set E, right? So that means what's left is less than a half what we started with. So this is less than or equal to half times the measure of Rn plus k, which is m-intercept Br0. By the way, I'm cheating you a little bit here, not really, but I'm fudging notation a little bit here. I said it was a Lipschitz graph, but the axis is the axis pi j, so modulo an orthogonal transformation that takes pi j to 0 cross rk, it's a Lipschitz graph, right? So this is all correct modulo, so actually it really, to be completely correct, I should have said q of the graph of a Lipschitz function with slope less than 4, where q is an orthogonal transformation. Because this would only be literally telling you that it's the graph of a Lipschitz function if pi j was in the vertical direction, right, in the direction of 0 cross rk. But that's okay. So finite union of orthogonal transformations of Lipschitz graphs would be that. But then you're done, because you can now repeat the whole process starting with m minus this, and just iteratively at the kth step you'll get less than 1 over 2 to the k times what you had before. So iterative process, iterate, implies mu of m intersect Br at 0 minus a countable union, because you've got to iterate for each k and then take the union of all of them. So a countable union of orthogonal transformations of Lipschitz graphs. Is equal to 0. So that says exactly that m intersect Br hat is m intersect the open ball of radius r is a n rectifiable subset. So that's the end of the proof. So a little bit technical, but I wanted to give that proof because it's a really good example of something that needs more synthesis than just starting and using some definitions. It's actually very clever. I'm not sure who originally realized this proof works out. Maybe Federer, I'm not sure. Okay, so that's the main. So now we've got several ways of looking at rectifiable sets. And let me finish by pointing out that we can now do calculus using the last characterization of rectifiable sets in terms of approximate tangent spaces. We can now do calculus on these sets. So let me just make that clear. So that is, so what we proved is that m countably n rectifiable is equivalent to Txm, the approximate tangent space, exists almost everywhere. And of course, we're still in the setting, as we have been for most of today, we're still in the setting where m is Hn measurable and Hn m intersect k finite for every compact k. So that's what we've got now to work with. And a claim, also remember the other fact that I started off with earlier today. Recall that you can write m equals union j equals 0. So this is an additional fact. You can write j equals 0 to infinity mj, where Hn m0 is equal to 0, and mj, and this is a disjoint union, and Mj is contained in Nj, where Nj is this n-dimensional C1 submanifold. So you can also do that, and we checked that Txm equals Txm exists and equals Txnj for Hn almost every x in Mj. So they're the main things. These are very useful properties. And I want to show you now that you can do calculus with these things. So, well, we already did calculus when we were working on Nj. So assume that U is open and contains M, right? And suppose that you've got a Lipschitz function, Fu into Rp for some P. Well, recall that we proved that the directional derivatives of F at a point X exist and are equal to ddt of Fx plus t times tau, evaluated at t equals to 0. And that's all correct, that there exists a set of measures 0. Let's call it Ej, contained in Nj, such that this exists for every tau in the tangent space of Nj, and for every x in Nj minus Ej. You only have to leave out a set of measure 0, then all of these things exist, and it's linear. This guy is linear in tau. Remember, we proved that for the C1 submanifolds. We already did that. So now, but this is great because our Mj is contained in Nj, and Txm is equal to Txnj for Hn almost every x in Mj. So that means that for every x, so for almost every x in Mj, we've got a similar thing. Same thing holds. d tau fx equals dd tau ddt fx plus. It's the same quantity. It's computed relative to Nj, but it now applies to M because of this. So we don't. It's sort of, you get something for free here, more or less. And that's true for every tau now in Tm x, and it's linear in tau. So you can then proceed exactly as we did in the C1 case, but now we're working on the rectifiable set M. And we can prove gradients exist almost everywhere. We can prove the area formula, co-area formula, without doing any further work. They follow directly from the C1 case because of this. So I'll talk about that in a little bit more detail next time.